Hi, everyone. Welcome to the Federated Wireless Showcase on bringing spectrum sharing to the 6 gigahertz band. I'm Jennifer McCarthy, Vice President of Legal Advocacy for Federated Wireless, and with me is my colleague, Kurt Schabach. Let him introduce himself. He's our Chief Technology Officer, an all-around guru. We appreciate you joining us and look forward to talking about how we are leveraging a lot of the technology solutions and know-how that we developed in the CBRS band in the United States and applying that to the 6 gigahertz band to enable sharing between new unlicensed devices, whether those are Wi-Fi or 5G NRU or some other technology, and the incumbents in that band, the majority of which are fixed point-to-point microwave links. A lot easier to share, we think, with those fixed users than with the military shipborne radars that we have in the CBRS band. But a lot of the same lessons that we've learned at CBRS are applicable to 6 gigahertz as well. And so we're really looking forward to enabling new broadband services to operate at 6 gigahertz with that shared capability. Kurt, to that point, maybe you could talk a little bit about the history of the CBRS band and what went on there, and some of the differences between CBRS and 6 gigahertz, but yet how we were able to take a lot of the same technology and solutions from that band to 6 gigahertz.
Sure, thank you, Jennifer. And again, nice to join you all virtually. So really the CBRS band began in the US in 2009. The Obama administration convened a panel of experts called the President's Council of Advisors on Science and Technology, or PCAST. And part of that process to look at ways to revive the US economy and implement industrial policy was related to spectrum sharing, creating a pipeline, a more fluid pipeline, more vibrant ecosystem for spectrum in the US to encourage economic growth. And the advisors from that council and process actually advised that spectrum sharing would be a way to accelerate accelerate spectrum availability and increase the pipeline of spectrum, because traditional methods of relocating incumbents, repurposing the spectrum through a regulatory proceeding and then auctioning the spectrum was taking up to a decade. And the costs of relocating incumbents was very, very expensive. So from that really was born the CBRS band. That committee as well, working together with the NTIA and the Department of Defense here in the US, identified 150 megahertz of spectrum that was really ideally suited for implementing the next generation of spectrum sharing. Spectrum sharing isn't exactly a new technology. We've been sharing spectrum in all sorts of different ways. On an exclusive license basis, we share spectrum through different geographies where every user has or licensee has a specific geography that they're permitted to operate within. Sort of a very, crude form of sharing, but still sharing nonetheless. And unlicensed bands where devices rely on a contention-based protocol, such as a listen before talk capability, to identify when spectrum is available for them to transmit. What we've done in the CBRS band is unique and novel because what we've done is applied cloud technology. And we've taken cloud and the massive scale and compute capability of cloud and used it to effectuate sharing in a very deterministic manner. So what we do in the CBRS band, which is really sort of unique, is on a real-time basis, we're constantly computing things like RF propagation for devices that are connected to this cloud platform that provides shared access, and doing things like interference calculations to identify what are the optimal assignments of spectrum for users in a given geography to achieve the two goals of making sure incumbents are protected and making intensive use of the spectrum on a shared access basis. And so far in the US, it's been a huge success. We're we at Federated are super excited about how things are coming together with CBRS now almost a year into commercialization. and we're seeing the sort of exponential growth that we had hoped for and predicted several years ago when this whole process first began.
Yeah, I was just on the CBRS panel, and we were all very happy to see how much growth has occurred there, and 0 reports of interference to incumbents, which I know the NTIA and the Department of Defense are very happy about. We were even suggesting that maybe the protection criteria might, be revisited, and/or the power levels within the CBRS band could be reconsidered, given the success we've had so far, and that might be a way to harmonize across the 3 gigahertz band in general. So
just
maybe
Jennifer, a quick point on those 2 things, and this is really to just drive home the power and flexibility of using cloud technology, is that a change in power limits, a change in protection criteria, we can just implement that in our cloud platform, and it becomes instantly available for every user. Not like something where it requires new equipment, new capabilities to be implemented, which sort of a legacy sharing technologies would have been very challenged to sort of implement this, to provide this flexibility that our cloud solution provide.
Absolutely. It's a really flexible tool. And that actually leads to another great point that'll transition well to 6 gigahertz, is not having to change the equipment. And how this database sharing scheme differs from, say, the TV white spaces, which was an earlier version of database-enabled technology, but one that may not have been as successful as CBRS is proving to be, and that we hope 6 gigahertz will be. Maybe you could elaborate a little bit more on the importance of not changing the equipment on the ecosystem.
Sure. Yeah. So one key aspect of CBRS is that there's actually these 2 tiers of use: a priority access tier and the general authorized access tier. The difference between those two tiers is one tier, priority access, has a quasi-license scheme. Users get a prioritization over other users when there's contention or congestion in the band. And then general authorized access tier, which is very much like a unlicensed approach, meaning the users don't require an explicit license to use the spectrum. They just have to connect to a cloud platform like our spectrum access system to enable sharing. What is really significant, though, with what we do with the general authorized access tier is we can really schedule uses. We can assign uses based on transmit power, bandwidth, frequency, in a way where users in a given geography are highly unlikely to interfere with each other. And it's the power of that cloud platform, the fact that we're computing RF propagation for every node that connects to our system, organizing these spectrum segments, allows for standard off-the-shelf 4G or standard off-the-shelf 5G technology to be used in the band. There's not the need for a special contention protocol or other capability for users to coexist in the band. And it's that function that, through cloud rather than through design, we're able to effectuate sharing, is what makes it possible and made it possible to tap into a massive global ecosystem of LTE technology that could be readily applied and used in the CBRS. And today we really we have, really acknowledged, we and others have acknowledged that the CBRS band today represents the largest ecosystem of LTE technology in terms of the number of equipment suppliers and device suppliers. And it's because of the standards-based aspect of the equipment and the devices itself, which make it so easy for other companies to participate.
Yes, exactly. And in terms of applying those that same capability to unlicensed devices, such as Wi-Fi or 5G NRU to the 6 gigahertz band, I think that's one of the important things that people may not understand is the automated frequency coordination capability that the FCC is requiring for standard power and outdoor devices that will operate on an unlicensed basis at 6 gigahertz. What the impact of communicating with the AFC will be on the equipment, if any.
Yeah, so the difference in the 6 gigahertz band is that devices will actually operate through this, more traditional, in US we call it Part 15, unlicensed approaches where equipment like a Wi-Fi access point, a 6 gigahertz band access point, or unlicensed 5G would have some contention capabilities built into it to mitigate interference between and among users. So the principal function of the AFC in the 6 gigahertz band is to provide protection to incumbent uses. Certainly it can help with coexistence of these new shared access users, but our focus in building the AFC is to assure the various incumbents that are operating in the band that they get full protection from these new shared access users. But much like CBRS, really identically to CBRS, there is no special, additional capabilities that are really required for devices to be managed by an automated frequency coordinator. What happens is through a very simple software API, devices can connect to the AFC, provide its location and other pertinent information that the AFC needs to use to do the interference check. And then the AFC reports back with what channels or what portions of the band are available for a device to operate on. And that software protocol is, for example, not unlike the software capabilities that every Wi-Fi device has to go get a firmware update, for example, from the manufacturer to keep their firmware or other software fully up to date. And devices could use things like an auto installation capability from a smartphone that would provide a GPS location that could be placed on the device or shared with the device, the RLAN device, and communicated to the AFC to indicate position and other pertinent information for those interference checks, as I said. So really, the AFC, I think, provides a very simple capability, again, all software oriented, that will really help open up and unlock a tremendous amount of spectrum in the 6 gigahertz band.
Yes, thank you. Yeah, I agree. The real benefit here is not to change the hardware requirements, but to base this all on software, as is the automation capability being in the cloud, which I think is really important, rather than resident on the device. And taking up, important computation capability on the device, or memory or storage. Maybe you can talk a little bit about, I know we're going to get into it when we show the 6 gigahertz AFC demo in a couple of minutes, but some of the computational requirements for administering the AFC at 6 gigahertz, and given the large number of incumbents that we have, and trying to figure out how to manage all of those protection calculations that are necessary. Maybe you can talk a little bit about how the cloud is an advantage for that.
Sure, yeah, and actually our implementation for the AFC is covers sort of two key aspects. One aspect is we do a lot of offline computation, which increases the efficiency of the cloud interactions, allows us to provide, instantaneous responses to a device when it makes a channel availability request. And we're able to do that because all of the users in the band, or the primary users, for example, the 100,000 fixed links, point-to-point microwave links that we're protecting as incumbent uses, are registered in a FCC database. We interact with that database. We pull down the licensee records, which include all the technical data that we need to compute protection contours around those incumbent users. And those protection contours are computed offline, stored, and then leveraged for these real-time calculations for each RLAN device. And there's different ways that the RLAN interference checks could be performed. One way is, for example, to ascribe an area around the RLAN device, which accounts for both the RLAN service area, how far the node, say the Wi-Fi access point, will be able to cover and serve end users, which is important to understand where interference might occur, and some uncertainty factors that can be added into that polygon around the RLAN device. Uncertainty factors related to maybe the positional accuracy that's reported for the RLAN device. If a GPS fix is not available, our system could work with really any form of geolocation, like a street address. And we could assign a different uncertainty factor around the device when we're doing these interference checks. So very flexible, very efficient. What's really important is when you put it in the cloud, you create the ability for massive scale. And that's obviously very important when you think about potential for millions, tens of millions of devices to be operating in the band and maybe needing to do these interference checks on a very routine basis.
Yes, I think someone asked me on a panel at the Wi-Fi Now conference last week about whether or not we'd be prepared for the scale of the Wi-Fi industry as opposed to the scale of an LTE band. And it was good to mention the cloud-based capability and how that will help facilitate the scaling that's necessary for that many devices.
That's right. And for example, all of the transactions that occur between the devices and the AFC in terms of the API are very similar to normal web transactions, a variety of HTTPS web calls. So we're leveraging all of the scale and capabilities, not just of cloud computing, but of the internet as a resource itself.
That's great. So why don't we turn to the slides now, if that's okay, and we'll walk quickly through this because I think this was covered on the earlier 6 gigahertz panel in a lot of detail. But if we could go to the next slide, please. So as Kurt mentioned and was discussed earlier today, the FCC this spring adopted new rules to allow unlicensed devices to start using the 6 gigahertz band, which actually runs from 5.9 up to 7.1 gigahertz, 1200 megahertz of spectrum in total. The use of an AFC capability, automated frequency coordination system, is mandated for standard power and outdoor devices in order to enforce protection for incumbent users. The majority of whom, as I said, particularly in uni bands 5 and 7, are these fixed point-to-point microwave links that are used by a lot of the mobile network operators for backhaul, as well as utilities, public safety, transportation. We got a wide range of folks who are using this band, and we want to make sure that their use is protected and can continue unfettered as they continue to grow their systems, at the same time that we're making any unused spectrum available for new unlicensed services. Next slide, please. Some key technical differences here between the low power indoor devices that do not need to connect to an AFC and the standard power and outdoor devices that do. The FCC's rules have very different power limits, including power spectral density limits. Those low power indoors literally are supposed to operate indoors only, and they must operate using contention-based protocols. They cannot be in weather resistant packaging, and they must connect to powered power source. They cannot be battery operated, and they must have a marketing labeling requirement that says that this is for indoor use only. The requirements for standard and outdoor power are much more forgiving and flexible. They do need to require on a daily basis to a centralized automated frequency coordination system, as Kurt was describing earlier. And when they request connect to that AFC and request a permission to start operating on this spectrum, they must provide the AFC with some key operating parameters, including their geographic coordinates, their height above ground level, and the accuracy of that geolocation information. They also need to tell us what channel bandwidth they'd like to operate at and what power level they're looking to operate at. And that's the information that we will use to calculate whether or not there is interference potential to the incumbents, and provide them with a list of channels that would avoid interfering with those incumbents. Next slide, please. This is just a familiar map for those of you following the 6 gigahertz proceeding in the US that shows where the locations of these fixed point-to-point microwave links are. You'll notice a ton of them along the East Coast between New York, DC, and Chicago. A lot of those are the high frequency traders that are using these to communicate, or with the stock markets. We got quite a few along the West Coast as well, which is to be expected. While you see a lot of geographic white space here on these maps, there actually is white space even in these densely populated areas. We did a study in, I think, January of this year, where we looked at New York and San Francisco and Dallas to see, on average, what might be available for new unlicensed service use, given the nature of the microwave incumbents in those three cities that have very different topographies, but are all fairly intensive in terms of their incumbent use. And what we found was that on average there was 700 megahertz of spectrum available for new unlicensed services, even in these most densely populated areas. So there really is a good opportunity here for new unlicensed devices to take advantage of this band while allowing those incumbent services to continue to operate and not have to clear them out. Next slide, please. So Kurt talked a lot about this. This is sort of our general architecture of how the AFC works, interacting with the FCC's existing universal licensing system database to get information that we need to calculate the protection contours for the incumbents from that database. We also need to interact with the new unlicensed devices, and as I said earlier, get the operating characteristics for their particular location and requested channel size and power level, and use all of that plus terrain databases and land use information to calculate what spectrum is available in a particular location without causing interference to any incumbents. And again, we are under the FCC's rules going to be communicating with each AFC controlled device on a daily basis to make sure that those channels are still available, that nothing has changed with regard to the incumbent use of the band, and to help try and guide the unlicensed devices to optimal frequency, availability, and usage that we can. Next slide, please. And we're going to go into this in the video that we're about to show you, the demonstration of the AFC that we've had up and running now, I want to say for almost 2 years, Kurt, when we first started working with the unlicensed community and the incumbents and started developing the AFC. So it's been quite a while that we've had this working. Is that right?
Yeah, that's right. We have, and we've built it for scale. It's ready to commercialize. Obviously, a key step in that process is going through some form of certification with the FCC. So they will have to test and approve an AFC system like ours for commercial use. And that is something that I know is under some discussion, debate within the industry right now. The FCC is beginning to, I think, turn their attention to this process, and hopefully that begins to accelerate quickly and we're able to begin full commercial use. Great.
Well, why don't we show the demo now, if we can. We've got a video where we pre-recorded the demo.
Wireless. After this technical slide detailing the AFC theory of operations, I'll then demo Federated's AFC. We've been working closely with the FCC incumbents and the unlicensed community over the past year and a half to develop and refine this operational AFC system. An AFC calculates protection contours around each of the more than 100,000 incumbent receivers using details such as incumbent transmitter and receiver locations and antennas as extracted from ULS. Federated's AFC stores in the cloud about 1,000 pre-computed contours for each incumbent receiver as the needed protection area increases as the requesting device power level and height increases. Higher power devices result in a larger protection contour, as is usually also the case with devices higher above ground, where, for example, losses due to clutter are less. More than half of the incumbent receivers use a 6-foot antenna, which is well modeled using the UHX-6 antenna mask. If the incumbent receiver instead used a 12-foot antenna, it would result in a narrower protection contour relative to what would be generated for a 6-foot antenna. For example, as shown in this slide, using the UHX-12 mask instead of UHX-6. To determine the spectrum availability for a device, the AFC first creates a circle around the device reported location with radius equal to its position uncertainty. The ASC then extracts from its database the set of nearby protection contours that match the device transmit power and height, and checks which contours are overlapped by the device circle, referred to here as the RLAN service area. If there's an overlap, then that incumbent's operating frequency is excluded from what is reported as available. The portion of the band that remains after this check is then reported back to the device as being available. Federated's AFC is designed with a user interface that emulates a request from unlicensed devices for spectrum availability in a particular location, given information such as the device location uncertainty, height above ground level, channel bandwidth, and transmit power. The emulator makes the request to the AFC using a standard and secure internet connection, gets the AFC response, and then shows on a map the reported incumbents needing protection, and plots the available spectrum. So I'll demonstrate availability in New York City, which is of interest as the incumbent density in New York City is high. Nonetheless, as we'll see, there's abundant 6 gigahertz spectrum for standard power operation. So first, let's consider a device in Manhattan with latitude and longitude as specified here. We'll assume full power operation for standard power devices, which is 36 dBm. In this case, we'll first assume that the device wants to operate using 80 megahertz. That translates to 17 dBm per megahertz. As there's still some discussion on the most appropriate building entry loss to assume for indoor operation, we also allow a penetration loss to be specified to the AFC. So in this case, the device is outdoor, so I'll set that value to 0. A typical device will be down in the clutter, most commonly around 3 meters, which I'll enter as the height above ground in this case. Per FCC rules, we'll use an incumbent protection criteria of -6 dB for the interference to noise power ratio. And for demonstration purposes, we'll also assume each incumbent receiver is modeled using a UHX-6 mask. Ultimately, the AFC will use the antenna make and model information in ULS to determine the antenna pattern. However, as the current ULS information is somewhat inconsistent, our current AFC release allows us to manually enter in the antenna pattern to assume for all incumbent receivers. And again, here we assume UHX-6. So in this case, we find that 1200 megahertz of the band, all 1200 megahertz, between 5925 and 7125 megahertz, is available for standard power operation. Our AFC currently reports all of the bands, all the uni bands between 5 and 8 in terms of their availability, not just Uni 5 and Uni 7 as per the FCC's newly adopted rules. So in future releases, we'll show just Uni 5 and Uni 7. But with that said, in this case, we see that the whole band is available and incumbents are protected throughout. So let's suppose instead that we wanted to model availability assuming a 20 megahertz channel instead of an 80 megahertz channel. In this case, 36 dBm translates to 23 dBm per megahertz. And to save time, I ran this case earlier and saved the result. In this case, we see that 950 megahertz of the 1200 is available, including all of Uni 5 and Uni 7. So looking at one of the Uni 8 incumbents, we kind of see a typical protection contour. For example, in this case, the device is shown here in red, and the incumbent protection contour for a receiver that's located a little bit to the north of the device location is as shown here. In this case, the transmitter is actually located down in New Jersey. But we see typical protection contour where it's long and narrow spatially, starting from the receiver. And again, if we had used UHX-12 instead of UHX-6, the antenna pattern would have been even more narrow. So continuing on, let's suppose instead that we wanted to put the 20 megahertz device above the clutter. Let's just say instead of 3 meters height above ground, we'll use 100 meters above ground. So even in this extreme case, we still see some Uni 5 availability around 6200 megahertz and some Uni 7 availability around 6700. So let's just look at one last case. Suppose we wanted to characterize indoor operation. So suppose we wanted to go back to 80 megahertz, and in which case, we use standard power, full power operation, and that gives us 17 dBm per megahertz. But now in this case, I'm going to assume the device is indoor, and I'm going to add a building entry loss of 15 dB. So in this case, we see much greater availability. More than half of the 1200 megahertz is available, including large segments of Uni 5 and large segments of Uni 7.
Great. Well, I'm glad we were able to show that demo, and I hope everyone was able to see what was going on the screen there. Obviously, that graphical user interface that we've been displaying there is not what's going to be needed by the unlicensed devices to communicate with the AFC. It will all be happening behind the scenes without all that manual entry, but we thought that that was a useful way to demonstrate the capability to we humans. One of the questions, Kurt, that we got in the from the audience was about the incumbents and whether or not we needed to relocate them or move them to another band. And the beauty of this is we don't, that they can continue to exist and add or change to their operations as needed. Maybe you can talk about the protection criteria that was established by the FCC and if any tweaks might be necessary. If we find through practical experience that there is interference where it wasn't expected and how we might change that, or if we start to notice a pattern of no interference, could there be an opportunity to relax that restriction?
Right. So thanks, Jennifer. The FCC did set an I over N criteria for protection of the fixed links, minus 6 dB I over N, if I recall correctly, and that is used for calculating those protection contours that you saw from the demo that Sam McMullen just provided. So the protection contour is calculated to find the furthest point from the fixed link location where the 6 dB I over N is satisfied, and then we draw a contour around that we use for the channel availability calculations. Again, the beauty of doing this in the cloud is that if we modified that protection contour, we could make adjustments on the fly. Those adjustments could be effectively pushed out to devices very quickly, so long as those devices routinely check in with the AFC to get channel availability information. If they check once and don't check back in, it's obviously much more difficult to adapt the sharing environment or provide additional protections or relax protections for the incumbents. But some form of closed loop operation really makes the system much more efficient.
Yes, thank you. In terms of whether or not this capability could be implemented in other countries, say throughout Latin America, I know that quite a few countries are considering launching consultations to possibly make the 6 gigahertz band available for unlicensed use along similar lines to what the FCC has decided or what Europe is currently considering. And that includes Brazil and I believe Mexico, Colombia, other countries are all taking a very close look at this and are thinking about moving forward. What are some of the issues from your perspective about this database-enabled sharing and things that the regulator needs to keep in mind to make sure that the database capability is going to work? I know that even in the U.S., our database on the 6 gigahertz incumbents is probably going to need to be updated, and that Sam, our chief architect in the video, alluded to the fact that having specific information about whether or not you're using a 6 meter antenna versus 12 was very important, and that we need to have accurate information to make this all work. But maybe you can talk about what some of the other things that regulators need to keep in mind in order to implement this capability in their countries.
Sure. Jennifer, you hit on the key thing, which is, of course, making sure you've got accurate information about incumbents and that you can share that information. Your your country's regulations or the policies around access to that data is such that whatever entity or entities are operating AFCs are able to interface with the database, access the information, and incorporate it in their analyses. Another factor for regulators to consider is whether they want to create an open market where multiple providers of AFCs could come get certified or approved to use their system in country, and then compete for share of market. Another alternative, obviously, is to have the regulator itself, develop the capability and implement and run a single AFC or AFC capability on behalf of all, prospective users or uses of the band. Each option, I think, has, different merits associated with it, whether you want to pursue a more free and open market, whether you think your country has the, if you want it to be in-country providers, whether you have the technical wherewithal and sort of the market, competition factors that would encourage, commercially developed solutions versus, regulatory solutions or government or regulator-led solutions create more surety and control for the regulator, but it also creates a cost burden for regulators or governments to develop and operate those systems. So there is no, I think, clear answer in terms of which one to do. Each, again, has its sort of, different merits associated with it. The US has gone the approach of, allowing companies to bring their implementations forward, get them certified. That obviously creates the opportunities for equipment suppliers to bundle or more tightly couple the AFC capability with other capabilities that they might provide as part of their solution, like a cloud-based Wi-Fi controller or 5G, core capability for 5G NRU. So it'll be interesting to see, I think, how the business models evolve, how the different solutions evolve. But really, beyond accurate data, there really is not much else required to be able to either import or develop a solution in another region, presuming that the equipment, the technical rules that are set allow for equipment that is being developed globally to be, imported and used in a given country.
Yes, exactly. I think that's really important to emphasize here is that so long as this AFC capability is allowed in the country and the databases are available for us to interface with, whether that information is public or private, we can figure out a way to securely interface with that database and can start operating at standard power or outdoor operations, almost immediately. One of the other interesting things I think that regulators need to think about is enforcement as well. If there are issues that occur with interference, if the unexpected does happen, and this is something that we've had to deal with in the CBRS band, and that we're talking to the FCC about as well. Where is the burden of identifying the source of interference? Is that on the incumbent? Is that on the regulator? Is that on the unlicensed device operator? And what are the advantages of connecting to an AFC in order to correct for or mitigate any interference should it occur, which we don't expect to do so, but in the event that it does, and there are always chances that could occur, why does the AFC bring some advantages from that perspective?
Right. Maybe I'll take the second part of that question first, since that part, I think, what really highlights one of the key capabilities or resources that an AFC could provide is to help in interference mitigation and even potentially sort of enforcement actions, beyond just the more routine process of, eliminating interference to incumbent uses. Particularly if the AFC has this capability where devices register with it, every device registers, every device provides its location and other pertinent technical information. And we have some means of communicating with those devices on an ongoing basis, that there's some sort of heartbeat or keep alive or check-in process that allows for the AFC to, and the devices that are already deployed in operation, to continue some form of communication. Having a sort of the complete ensemble or population of devices that are in operation, in addition to this sort of closed loop operation, allow for very efficient means of interference mitigation. We could change protection criteria. We could identify geographic areas where uses are temporarily suspended on a particular channel or a range of frequencies until maybe an interference event is further diagnosed, triaged, and resolved. Tremendous number of tools, automation available with the AFC, which regardless of where the responsibility lies, whether it is with the end user, the equipment supplier, the regulator and its enforcement body or entity, or the AFC operator or some collection of those entities, when you can automate this, it really sort of reduces a lot of the burden on all of those parties, obviously provides a lot more surety to the incumbents. Those things, I think, are some of the key arguments or benefits that the AFC could provide.
That's great. That actually leads to two final questions. One has to do with how we're factoring in the antenna pattern of the incumbent receiver and side lobe, back lobe, things of that nature. And then the second question I would pose to you and leave with the audience is the complexity of database solutions and how folks think that it's really too complicated and too expensive and too much of a bother to implement, and maybe the difference between the CBRS sharing mechanism, which is definitely more complicated than what we're talking about for 6 gigahertz. But maybe to the antenna question first and then to the complexity issue.
Yeah. So the antenna question, what we do today is we use a antenna mask, and that mask accounts for both main lobe, side lobe, back lobe characteristics. But it is, if you will, a proxy or surrogate for the actual antenna in use. It's a mask that is supposed to capture, here's what a 6-foot dish normally, how its radiation characteristics normally look. Now, obviously, we could incorporate real antenna data. If that information was made available in the FCC database, we could have a library of antenna patterns and be able to access those as part of our computation. So it's really no added complexity to account for the real antenna pattern versus an antenna mask, a pattern mask. The key thing is really the burden, if you will, on licensees to provide that information and have it accurate and updated in databases. Regarding the second question, Jennifer, on complexity, there is really a broad range of complexity that could be implemented or considered. As you said, CBRS is maybe at the far end of the complexity scale because we're doing things like aggregate interference protection, which require systems to peer with each other and exchange a lot of technical data in order to assure that every device is calculated and included in protection to incumbent uses. Also in the CBRS band, we have mobile uses, which and the DoD is a primary mobile user, shipborne radars that require a very different protection methodology than, say, fixed incumbents that we have information from a database that we can acquire and provide protection to. So the AFC is really much simpler than what we have had to do in the CBRS band. And we can, continue to provide further simplifications. It really comes down to the questions about how intensively do you want to share spectrum? What is really the requirement for providing, sufficient incumbent, protection of incumbents? There's lots of different ways to do this, which all have different implications on system complexity. So I think we've really found a great balance in both the CBRS and AFC 6 gigahertz band with the SAS and the AFC, and different tools, and different requirements to address different incumbent scenarios.
Well, thank you, Kurt. I think with that, we are at the end of our time, and we'd like to thank Forum Global for inviting us to participate in this America's event and for giving us the time to showcase our 6 gigahertz AFC, which is ready to go commercial, just waiting on certification by the FCC, and for industry to be ready to start using this spectrum. And we're very happy to talk to other regulators or prospective unlicensed device operators in other countries and see how we can adapt this capability if necessary to your unique circumstances, and help you start making more efficient use out of the 6 gigahertz band. So thank you to everyone and have a great day.
Great, thanks so much.